Ladies and gentlemen, very welcome. All right, let's go. So last time we covered way less material than I wanted to, but on the other hand, we had way more discussion than I had hoped to have, and you really do ask great questions. So I was happy to invest that time. And now we will continue with what I didn't have time to cover last week. Namely, we will continue with decision trees and move on to random forest. And depending on our discussions, we'll do more than that. Okay? So where did we stop last time? We saw how to construct a decision tree. And I ended with a list that I had entitled Arbitrary Choices. And after lecture, somebody asked me, what did I want to say with that? And, well, I wanted to point out the following. It really is a good method. So when you have little training data and finite computational resources, these decision trees are amongst the best thing that you can use. However, they are not, extremely canonical methods, and that's what I wanted to point out here. So there are many arbitrary choices, and I just wanted to highlight that, we do greedy tree, but we could, we could decide to do to try and find the optimal tree. Only it would be much more expensive, or yes, we decide to make the tree binary, but in principle, each node could have more than 2 splits, and so on. No? Good. Then the last thing I did last time was to name the impurity criteria, which we use when we decide where to split. And I've given the formula only for one of them, for the Gini criterion, which is the one that performs best in practice. Good. So this is where we stopped last time. And so today, I want to start by giving you a few more details on this tree construction. Now, when we try out all these different split positions, we have to somehow decide which one do we like best. And this priority for split candidates is measured by how much this extra split can reduce the impurity of all the samples that end up in this leaf node. This is another question that somebody asked last week. So when I say splitting a node, what do I mean? Well, a tree is composed of nodes, and the terminal nodes, which I here indicate with squares, they're also called the leaves of a tree. Okay, and I'm going to truncate here. And now each of, if you remember, in each of these nodes, we ask a question, like, am I above this threshold or below this threshold? And so each of these leaves corresponds to one region in space. So for example, the first node asks, are we above or below this horizontal line? Then the next node asks, are we to the right or to the left of this second split here? So I'm calling this here 1 and 2. This is number 1, number 2. And now in this second node, we may still have, very many examples. I think last time I did orange and purple. Good. So if we now make this decision here, this decision number 3 here, even before we make this decision, this node here, which I'm highlighting, let's say this one here, this node corresponds to all of that part of space, let's say. Yeah? And then, well, this node makes another split, namely this third, or this. All right. This node here will make that split. But before we make that split, this node corresponds to this entire region here of feature space. So this is the correspondence between parts of feature space and what we see in this tree on the right-hand side. And now when we try to decide where to put the split, so do we want to put it further up or further down, or do we want to use this split, or do we not want instead to use vertical splits? When we ask these questions, the recipe that we're going to use is the possible reduction in impurity that can be achieved. Yeah? So the priority for splits candidates is measured by the possible reduction in impurity. And in terms of a formula, we measure this as follows. I'm using the letter H here for the impurity measure. So this is the impurity of the node that we currently consider, impurity of the node under consideration. And now we look at the impurity of the children. So we are interested in the impurity of the left child, impurity of the left child, and we're looking, we'll leave some space here, and we're looking at the impurity of the right child. But if we only measured it like this, then we could have a problem that a split will decide to just shave off a single observation. So for example, in the picture up here, the decision tree could decide, okay, let's make, instead of this horizontal split here, let's make this vertical split. And then I have a perfectly pure left node, and I have a mixed right node. But on this, but in this left resulting region, this one here, we only have 2 observations. So if we do that, we will obtain trees that are very deep. Decision trees that will need very many levels before you reach a leaf node. And we don't want that kind of trivial solution. So instead, this entire these impurities are weighted by how much of the samples in the node do they actually process. And I'm going to write here number of left divided by number of left plus number of right. So this is all the samples in this node, and the same thing here. So this is here times number of right divided by number of left plus number of right. So this one is how many samples end up in the left node. Hash R is how many samples end up in the right node. And so this normalizes the impact. Yeah, was there a question or was it shaking off? Yeah.
The samples are not like super dense. I still have some degree of freedom, right?
Yes.
I could obtain the same numbers for a certain area.
Yes. So what you're saying is, let me zoom in here. If I make the split here or here or here, according to this criterion, will all be the same. Yeah? This is correct. So again, there are many recipes. I think a natural one is to just do it in the middle. Yeah? This is most akin to what a support vector machine would do. All right. So this is how to construct this tree. I think it's a simple enough recipe. You won't get as homework, code a decision tree, because actually it does take a few lines of code to do it correctly, but it's nothing complicated in principle. All right, and now I would like to discuss properties of decision trees. Let's look at the computational complexity. We will look at the computational complexity of tree construction, so for learning, and then also later for testing. Yes?
The H, the measure of the purity, how is this defined?
Okay, this is any of the functions that we looked at last time. So the question was, what is H? And H would be one of these three things, and other people have proposed more, but that would be one of the three. Thanks for clarifying. So today we've called this H. Good. So the computational complexity of constructing a tree. And now in this discussion, we'll restrict ourselves to these monothetic decision trees. You remember the word? Those are the decision trees which make axis orthogonal splits. So first, at the root node, or level 0 of the tree, remember what we do. We have a big loop over all features, because we try out how good is splitting along each of the features. And then for every feature, we have a loop over all the split positions. And to find all these split positions, we need to sort the samples along that dimension. So we sort n samples, which, unless you make special assumptions, will have a cost of n log n. And we have to, and then for each of these positions, we try out or we measure our impurity. And we need to do that according to each of p features. By the way, measuring the impurity is just linear in the sample size. So we can say measure impurity for each split position. This is just O of n. And for those who have learned about these complexities, what matters is always the highest complexity. So if I have an operation which costs order of n, and an operation which costs order of n log n, then as n becomes large, the smaller will pale in comparison, and we forget about it. But we need to do this for each of the p features. Then what we get overall is O of p for p dimensions times n log n at the root node. Good. Now we make an assumption, namely that this first split puts roughly 50% of the samples in the left child and 50% of the samples in the right child. Yes?
And what does these p features mean? Are these the possible axes along which you can split?
Yes. Yeah. So you remember we have talked about this data matrix X, which was p times n, and p were the features and n was the number of samples. And well, we have not looked at many practical examples yet. So when we were discussing, I've mentioned a few times this electrocardiogram classification example. There we have a few seconds of signal, and then we multiply this with the sampling rate, and then this gives us so many hundred features. Or let me fast forward to an example I want to give later. Here, we try to classify magnetic resonance spectra. So what you see here, these are so-called chemical shifts. So we have, for each substance, a spectrum, which is not shown here. But each spectrum is characterized by 1,500 channels. So in this case, each magnetic resonance spectrum would have a P of 1,500, and then, well, in this case, I think these were spectra of red wine or something. If you have 5 red wines of this type and 5 of that, then P would be 1,500 and N would be 10.
So just to be clear, there is P times N possible splits, right?
Yes.
Because you wrote O of N. I mean, it's O P times N, but this is still like this.
Yes, you are right. I tried to say that. So along one dimension, we have n, and then we do that according to each of p features. We agree. Yeah. Good. Now let's assume that each child of the root node receives half the samples. And this is, an unjustified assumption for now. I will justify it later. Then we have, in level 1 of the tree, we have the left child and the right child. Yeah? So the left child gets P times n over half log n over half. But the right child gets the same thing. Yeah, so altogether, we get 2 times P over n half log n half, and this cancels, the 2 cancels, so overall we have P times n times log n half. Now at level 2 in the tree, we can recurse this argument. At level 2 we have 4 nodes. So it's, I'm now repeating this formula here, just with 4 nodes. And each of these 4 nodes will have a quarter of the samples. And so on. So this time the 4 cancels. And if we continue the argument, we find that for a balanced binary tree, so binary tree means that each node has 2 children, and balanced here means that there are no, so that all leaves are on the same level of the tree. In such a balanced binary tree, if we always evenly partition the data between left and right child, we'll have LGN levels. So LG, this is the 2 logarithm of n. Yeah, so for example, the 2 logarithm of 1024 would be 10. So for a balanced binary tree with LGN levels, the overall training cost or complexity is O of P times N times the 2 logarithm of N squared. Why? Because here we had, so from level 1 we had P times N times, okay, I should start at level 0. At level 0 we had P times N times the logarithm of N. And now we need to repeat this over log N levels, and hence we get this overall complexity that I've given at the bottom here. So in other words, this is cheap. Now, here we made the assumption that if each child receives half the samples, we have the freedom to encourage or enforce this behavior, because when we design our splitting criterion, we can always say that we bias our splitting criterion such that it prefers putting half the samples left and half the samples right. Yeah, I can easily do that by using one of the impurity criteria themselves, by the way, just not with class labels, but just with counting how much goes left and how much goes right. Okay, this was the training cost, or the training complexity. Let's look at the computational complexity of predicting. In the best case, well, the cost will be of the order of the 2 logarithm of n. Or let me not write order, let me just say the 2 logarithm of n. If my tree really always sends half the samples left and half the samples right, then if I have 1024 samples, then I need a tree of depth 10. So this is the best possible case. What would a worst case tree look like? Yeah?
O from n to the two co on n times n.
Can you describe the tree, what it would look like?
It would look like which is like just like one node with the next one like more like a singly linked list than as an actual.
Perfect. Yeah. So this is the worst case tree, which has, and it goes on and on. This split here shaves off just one observation. Yeah. So here we have associated with our first leaf, this one here, we have a regional feature space which contains just a single training sample. And then the next split, this one here, also just shaves off a single training example. Yeah? And so our worst case tree has a depth of n for n samples. Now we've seen the best case, we've seen the worst case, and the average case, actually, I don't know by heart, and I forgot to look it up in the literature, but the average case, I think, is pretty close to log n. So the trees usually are not, the trees that we find usually are not very imbalanced. So, in other words, cheap. You know, if you remember one nearest neighbor, for every prediction, we had to look at all, you know, find the nearest neighbor. And unless we use special data structures and approximate nearest neighbor finding methods, etc., this would cost O of n. And here we have something that's more like the logarithm of n. So it's super fast. Good. Let's talk about the splits themselves. What are the properties of these splits? I've said a few times now that the most popular splits are axis orthogonal. So axis orthogonal splits ask questions that refer to a single feature. Let me go back to the picture from last time. So here, our root node asked, the root node of this tree asked, okay, I have a query. Is this query, does it have a feature value 1 which is bigger or smaller than 0.5? That was the question at the root node. And then we get a similar question at the next node and so on. So here, just a single feature is considered at each node. This is what's meant by axis orthogonal. No? Now, these axis orthogonal splits, one thing that's good about them is they don't have this problem like k nearest neighbors of us needing to find a good scaling of the axis. So good, it's invariant with respect to scaling of the axes. So let's say we've measured, one feature in terms of grams, and now the other feature was a length. And here we had this choice: do we use meters, or do we use kilometers, or light years, or something? And now in decision trees, all that we do is we sort these samples, and we don't care. So these impurity criteria that we looked at, as long as you consider a single feature at a time, they don't care about the units that you attach to the axis. So this is what I mean by it's invariant with respect to scaling of the axes. What's bad is for correlated features, we will need many splits. Let me give you an example. So I have two feature axes here. I have two data sets, which in principle are very easy to separate. I have the purple examples here, or excuse me, the orange examples here. I have the purple examples there. And we see that, well, the optimal axis here, should be something like that. A single split would perfectly separate the two classes. However, if I restrict myself to axis orthogonal, well, you see that I will need very many splits. I can start by splitting here, and then splitting maybe there, and then splitting perhaps there, and then here, and so on. Yeah, so I've needed that many axis orthogonal splits. Now the first kind of split that I showed, I've already mentioned briefly last time, is called an oblique split. So here the kind of question that we would ask in a node is not, is my feature x7 greater than 0.3? Here this was just asking the seventh feature, but in such a tree I ask, is the inner product of some weight vector in my x larger or smaller than some number? Yeah, so now x is a vector of all features and w is a weight vector. And such oblique splits are also pretty, well, I would say it's the second most popular class of splits. And here's an example of, on the left-hand side, of what such oblique splits could look like. And this figure I've grabbed from a paper by Thomas Hehn. I've grabbed it because he was sitting in one of those chairs not so long ago. And he wrote this paper as a diploma thesis in my lab, which was about differentiable decision trees. So far, I'll come to your question. So far, we've constructed this tree greedily. We've made these splits one after the other, and once a split was made, we never touched it again. But we could decide to make these splits, first this one, number 1, number 2, number 3, number 4. This was a greedy construction. And now to relax the thing and let those splits readjust to better fit the data. That would be a differentiable decision tree, and this worked very nicely. And so he actually got the best paper award from the German Association for Pattern Recognition for this work, which he submitted there. And that's an example of oblique splits. Yes?
So first question is, if we would then maybe also diagonalize the data again to find the eigenvalues, and then it would make sense to then make the decision tree happen?
So the question was, how about doing something like PCA first? So to do this on a whole data set, it would work in this particular example that I've done here. It would no longer work. It would work in this particular example. Yeah? As soon as we start having nonlinear dependencies, that will not work. But when we do discuss now criteria for finding such oblique splits, there's again a huge choice. We could do something like linear regression in each of our nodes, or we could do some kind of regularized regression. I will say more about what that is later in the lecture. And in fact, one pretty good regression method is to first do principal component analysis and then do regression in the subspace that you find. So you could do this actually iteratively in each of the nodes of your tree. That works decently.
Okay, and the second question is with the differentiable trees, if we just take a tree and then smooth it out, we do it like, well, if we do another thing to smooth it out, we have like a smoothing kernel along the cuts.
So are you saying that there's an extra parameter by how much you smooth? Is that what you're saying?
Yes, or how is the method to smooth it out in these trees?
Okay. So here, something similar to a logistic regression was used along each of those splits. And indeed, there is this parameter that you refer to, this beta, which says, how much of a step function or how smooth is it. But the nice thing here is that in the end, you do get out a decision tree. So at test time, the predictions are crisp. Yeah, so you smooth it during training to let the thing readjust. But once done, you make it crisp. And conceptually speaking, the beauty, and this is why I like the question of this, is that a single query will walk down a single path of this tree. So it means if you are on hardware with very strong limitations, this is computationally much sparser than a fully probabilistic method or a neural network where each sample is propagated through the entire method. So that's a strong argument for these trees. Now the argument against is that if you look at real-world hardware where the development of smartphones and so on goes, they are getting ever more powerful GPUs in there, and GPUs are good at parallel processing. So for a GPU, it's fine to use all these streams at once. And if you do use a GPU, your main concern is that you want your computational graph to look very uniform. Yeah? So you want, this is not going to be a nice picture. So this tree here, for example, it was not uniform. Huh? So one leaf was split, so it was not a complete tree. And when you do things on GPUs, you want all computations to be very similar. Yeah? So I would say currently the where all of this is heading is to use GPUs and neural networks. However, for these neural networks, you always need lots of training data. And that's still a beauty of these decision trees. If you have very limited training data, that's still the best thing there is out there. More questions? All right. Then we're still discussing properties of decision trees. I want to point out another one, namely decision trees are likely to overfit. And do I have a picture? No. So let's say we have our orange class. We have our purple class. Okay, so the consensus, I think, is, or if you ask me, I have to train a classifier, what should it look like? Yeah, we have the orange samples on the top left corner, and we have the purple ones on the bottom right corner. So the kind of classifier that I would draw here, given two features, given the size of training set, would be maybe something like that. Or maybe I would just choose a straight line and say, this is my preferred classifier. But remember what one nearest neighbor classifier does. One nearest neighbor classifier would now, remember the Voronoi regions and so on, it would create tiny islands for all of these outliers here. And similarly, if we really train a decision tree until purity, then it will start using very, very many splits to explain all of these single observations. So, let me try and sketch. The first split is decent, the second one is good, and now it starts, the decision tree here will start, introducing more and more splits to account for each and every one of these observations. And now, would you believe any of that? Of course not. So if we get a second training set from the same underlying process, it would still look that, the orange samples are on the top left and the purple ones are on the bottom right. But where they lie, where these islands are, would of course be completely different for a new set of samples. But if we train a decision tree on the one set and if we train a decision tree on the second data set, we would get completely different looking decision trees. By different looking, I mean if we really look at the questions that are asked in the nodes, they would be different. So in statistical terminology, we would say that decision trees, just like one nearest neighbor, they are low bias. So in expectation across many data sets, they will do the right thing, but they are high variance. So if you give me one training set or the next, I will get different looking decision trees out. And well, whenever we have this, whenever we encounter high variance, we recur to regularization. I will explain in the context of regression, where this word came from. Initially, it came from, okay, you need to solve an inverse problem, and the problem can be singular or regular, and you can make it more regular, or you can regularize it by making certain assumptions. And now this term regularization has become completely, it's now used across all of machine learning. Whenever you want to stabilize an estimate, when you want to lower the variance of an estimator. Now, can you propose a way to regularize decision trees? We've just said the problem is that it tries and account for each and every training sample. Yeah. Limit the total number of splits. So I could just go on until I hit some number, and fine. Now, if I limit the number of splits, I also need I need some kind of prioritization. So do you want to build your tree top down, or do you want to always proceed by splitting the biggest remaining nodes or something like that? Yeah? And these are all legit methods, but we need, if we want to cap the number of splits, then we need one of those recipes also. It's a good suggestion. In the back. So you are saying, let's not make two splits closer than some...
For example, define where those splits can be made.
Yes. Okay. I think it may be tricky in high dimensions, but probably something could be cooked up along that direction also. There was way back. Some limit on so you would have some tolerance, yeah? So an impurity of 0.99 is good enough. Yeah, very good. Another suggestion. Yes?
Maybe weight the amount of nodes differently, like within the impurity, weight the amount of nodes. So if we have, okay, we get increased tolerance to impurity, but we have to get way more nodes than this might be biased. Then you've got a new hyperparameter, how much weight.
These are all good suggestions. Yeah. So the umbrella term for these would be early stopping. So we don't grow the tree until its maximum extent, but we somehow stop before. Yeah? So I'm going to write here abort if a node has too few samples, for example, and then we have this hyperparameter of, well, how many samples is too few. So we can come up with many recipes here, and every recipe that you come up with, somebody has already written a paper about it. Yeah? Abort if the node has too few samples, or if the impurity reduction is too small, whatever that means. Yeah, what does too small mean, or what does too few mean? We need to come up with some recipe. Yeah? Or there is a converse recipe called pruning. Namely, you first build the tree all the way, and then you cut it back. Pruning is a term from gardening. You prune roses. You cut off the superfluous trees. And people who know about roses, supposedly the rose becomes prettier if it has too many branches and you cut off some of them. Good. So overall, I would say decision trees, we have a limited theoretical understanding of these. They're super efficient computationally, and they are pretty good in terms of accuracy, but we have this low bias, high variance problem. We will address the high variance after the break. And for now, I just want to announce that next week on Monday, there will be no lecture because we are an excellent university, yay. And there's a lot to say about that. But we have this excellence cluster structures. Yeah? So I'm a member of that, and we have to do something together with colleagues in France. And so I cannot be here on Monday, and we will have no lecture on Monday next week. For now, have a good break, and we continue at 1:15.